Okay, everybody, good morning. I hope you've printed out your notes on Ohm's Law for today so that we can go through this. We're going to start by looking at a German scientist whose name was Georg Ohm. Now, Georg Ohm did a lot of work with different kinds of conductors, and because of that, they honored him by naming a unit of measure for him. We'll get to that shortly. Basically, what he did was he noticed that when he used conductors made of different metals, but they were the same length and the same cross-sectional area, he noticed that if the potential difference doing the work to push the charges through was the same also, then the current going through each conductor was actually different. Since they're the same length and the same cross-sectional area with the same amount of work being done to push the charges through, he determined that the difference in the current must be due to the two different metals. So basically, he said that every metal conductor has its own resistance to current. Some conductors have more resistance to current, and therefore not as much current can go through for the amount of potential difference doing the push. Some conductors have less resistance and more current can get through for the amount of push. This quantity resistance is an inherent property of the metal, and it doesn't change unless you change something about the conductor itself, such as its length or its cross-sectional area. Now, in AP Physics, we would actually look at the resistance of a conductor based on the physical properties. We don't do that at this level, though. So we're going to look at how you can use electrical measurements to determine the resistance of a given conductor. So let's take a look. First off, let's take one conductor, okay? And in this case, I chose to use copper. We're going to attach, say, a battery to the two ends of the conductor so that one is negative, attached to the negative electrode, one is positive, attached to the positive electrode. So the current, the electrons, will go from negative to positive, okay? Now, for this one conductor, if we change the amount of potential difference doing the work, for example, maybe we attach a 4-volt battery to the conductor, and then maybe a 6-volt battery, and then maybe an 8-volt battery, and each time we measure the current produced in that conductor, you'll notice that each time, no matter what the potential difference is, the current is proportionate. So, for example, if we have 4 volts, we have 2 amps. That's half of that, isn't it? If we have 6 volts, we're going to get 3 amps, which is half. And if you have 8 volts, you're going to get half or 4 amps of current each time. So I want you to notice that the potential to current ratio is the same every time. This ratio is basically the resistance of that conductor. A different conductor would have a different potential to current ratio. All right, it might be a third instead of a half. So the resistance can be measured by simply looking at the potential to current ratio. In other words, potential difference divided by current. All right, we use a capital letter R to measure, to indicate resistance in the equations, in the formulas. Also notice that this is a linear relationship. If we think rise over run, okay, then if we have the potential difference on the y-axis and the current on the x-axis, the slope would give you the resistance of the material. Now, anytime you have a substance like copper or gold that has a linear relationship between potential difference and current, it's called an ohmic substance. So copper and gold are examples of ohmic substances because the resistance is stays constant. The potential increases, the current increases proportionately so that you get the same resistance, the same slope. Now, there are substances that also have resistance, but the resistance changes with the amount of potential difference and current. And those are called non-ohmic substances. For example, a heat sink resistor. Heat sink resistors are non-ohmic. That is, they increase the amount of resistance as the current increases because current produces heat from friction between the electrons and the atoms. So you get a curve if it is non-ohmic instead of linear. Now, for our purposes, all of our problems, we're going to be using ohmic substances, not non-ohmic substances. So we can assume all the substances we use are ohmic, and therefore the relationship would be a straight line. Now, an easier way to look at this is to simply take the current, multiply it over, so you get the linear form, okay? V is proportional to I with R as the slope. So Y equals mx plus an understood B of 0. We call this, because Georg Ohm came up with it, we call this Ohm's law. This is like the Fermat of circuits. So I expect everybody to know this. Brand it on your brain, just like you did Fermat. This is the Fermat of circuits. Potential difference equals resistance times the current. I just say Ver, okay? Ver, Ohm's law. Now, if we go further down, let's take a look at the unit for resistance. Potential difference is measured in volts. Remember, big V is measured with little v, so volts of potential difference. Current is measured in amperes or amps, named for Andre Ampere. But they decided to honor Georg Ohm by naming the volt per amp of resistance the ohm of resistance. Now, we do not use a letter O to represent an ohm, and it makes sense if you think about the fact that if you had 10 ohms and you were using an O for ohm, it would look like that. So is that the number 10 or is that the number 100? So that would be confusing. So they went to the Greek alphabet and they used the Greek letter omega, which looks like an upside down horseshoe. So you would say 10 ohms, and that's how you make it. It's pretty simple. Just practice it a little bit, okay? And you're going to hear some more about that in the video tomorrow on resistance. Okay, now Ohm's law can be applied two different ways when you're talking about a circuit. If you look at the load of the circuit, remember, not the load, the source. If you remember, the source is where the battery or electron pump, whatever it may be, that's providing the potential difference to the energy to your electrons. You can apply Ohm's law to the totals. In other words, the total potential provided by the source equals the total current in the circuit times the total resistance of all the devices in the load. So VT equals IT times RT, Ohm's law for the totals. But the interesting and very flexible thing about Ohm's law is it can also be used on single devices in the load itself. For example, in the circuit we drew the other day, I think we had like a light bulb and a resistor and maybe another light bulb or something like that. Ohm's law can be used on the individual devices as well. Every device that converts energy in a circuit, you can use Ohm's law on. The potential it uses, the current that's going through it times its resistance. So one light bulb would have its own V, its own I, its own R. Another would have its own V, its own I, its own R. A third would have its own V, its own I, its own R. So that's why we use subscripts to keep them separate. Each device is assigned its own subscript, and we never mix subscripts. Now, that being said, it is important to understand when you label a diagram, that's when you assign each device that's converting energy its own subscript. What do you not assign? Well, guys, switches do not convert electricity. They transfer it, like a seatbelt transfers braking force to you. All right? So you would not assign a switch a V, an I, and an R because it's not converting energy. Likewise, measuring devices like voltmeters and ammeters, they are not converting electricity to other forms of energy. So you don't assign them subscripts either. They don't have their own V's, I's, and R's. They are simply measuring what's in the circuit. They are invisible to the circuit. Only devices that are converting energy are assigned their own numbers because they have their own V, I, and R. Okay. Now, let's actually create a circuit. And let's look at what we're going to have in it. In this particular case, we're going to have a circuit with an 8-volt battery in the source. So here's a symbol for a battery. Notice I drew 2 cells, not a single cell. So instead of 1 short and 1 long line, I have 2 shorts and 2 longs. They alternate so that you've got a short for the negative on one side, a long for the positive on the other side. So this is 2 cells. There's 1 cell, and there's the other cell, okay? The short line side is always the negative. The long line side is always the positive. So this is 8 volts. We also are going to have 2 light bulbs in the circuit. One of them uses 3 volts of potential because if you remember, light bulbs are converting energy. They take electric energy, convert it to light and heat. So here's one of the bulbs here. It has a potential of 3 volts. I'm going to assign it a subscript 1. So it has its own V, its own I, and its own R. Now, the other bulb, we don't know what its potential is, but I'm going to assign it the number 2. So it'll have its own V and its own I and its own R. We just don't know anything about it yet. We also want an ammeter in the circuit to measure the current, and we're told that this ammeter is measuring a current in the circuit of 2 amps. So we use an arrow to show which direction through the ammeter the current is traveling, and we label the amount of current in the circuit IT. Okay, so we have the total potential put out by the source. This bulb is using 3 of that, and we have a total of 2 amps in the circuit of current. We also are going to use a voltmeter to measure the potential difference being used by this unknown bulb, because that's what voltmeters do. They measure potential. And I'm going to show you now how we can create a circuit with these devices, correctly stick in our meters according to how they have to measure what they're going to measure, and you'll see it's not really all that difficult. So if you'll turn the page, and you might want to use colors for this, hint, hint. Okay, at this point, you might want to, hang on, you might want to stop the video and copy this down. You might want to pause it and copy this down, just like I have it here. Okay, now let's analyze what we've drawn. We have our battery. Now, interestingly enough, please remember, we always use squares or rectangular shapes to do circuits. Even electrical engineers do this, all right, because it keeps everything nice and neat and easily analyzed. Also, and I don't know why I do this, but I typically put the source on the left side of the circuit. Now, does that mean you have to? Absolutely not. You do not have to do it that way. You could put the source up here on the top and have the load on the bottom. You could put the source on the right and have the load on the left. You could put the source on the bottom and have the load on the top. That's personal preference. I just typically put my source right here on the left side, and then I typically go clockwise with my current. Again, I don't know why. And that means the negative side of the battery has to be on the top, because our non-conventional current, our electrons, always travel from high or negative potential around to low or positive potential. Okay? So electrons always go from negative to positive. So here's our total potential of 8 volts provided by the source. Now, the two bulbs, it doesn't matter what order you put them in, but I let the known bulb be the first one. So I have a V1. The filament in the bulb has a resistance R1 because it's a conductor, and there's some amount of current going through it we'll call I1. You don't have to label that though right now. Then the current comes around, it's going to go through the second filament. That one uses an unknown potential and goes through an unknown resistance. It meets an unknown amount of resistance in the filament. Then the current comes through, it gets measured by the ammeter, okay? Now remember, the ammeter is measuring the rate of current flow, not the amount of energy in the current. So it doesn't matter if you put the ammeter here, it doesn't matter if you put it here or here. As long as all the current goes through it, it'll measure the flow rate. And since it doesn't have to measure energy, that's why it doesn't matter where you put it. Now notice, labeling. Always label RV, RV, here's V, and here's I for this. Now, let's talk about our 2 meters for a moment. It's important that you understand why they look like they do. This one, notice the current all the current that's going in this line has to go through the ammeter to get measured. So it should always be on the line with the other items. But the voltmeter's a little different. So let's look at these. Okay, over here on the right side of your paper, you have some stuff. So an ammeter symbol is this. We already know that. And it measures currents in amps, milliamps, or microamps even. We always say that the ammeter is connected in series. Now you should know what the word series means. Series means a progression of items. For example, the Harry Potter series of books and movies. You got 1, 2, 3, 4, 5, 6, 7 for the movies, right? Actually 8 for the movies, 7 for the books. So a series means they're in a row, one after the other. Well, look at this. Our source, our first bulb, our second bulb, the current goes through each one after another. So this is a series of items. Well, the ammeter is just part of that series. So the current goes through the first light bulb, through the second light bulb, through the ammeter, and then back to the battery. So it goes through the series. Ammeters are always connected in series with the current being measured. Voltmeters are a little different. They're helping you to understand the measure of energy content that's being used from the electrons, the volts of potential difference, the energy per charge. So it does make a difference where you attach a voltmeter. We want to know how much energy per unit charge or how many volts are being used by this filament to convert electric energy to light energy. So we need to know how much energy per electron the electrons have going in and how much energy per electron the electrons have coming out. So you have to attach it where they go in, where they come out, so that you can see the difference between the energies per unit charge. That would be the volts. So what do we call this? Well, let's take a look. First, voltmeters measure potential difference, capital V. And they're connected, we say, there we go, in parallel. Now, why the term parallel is used for the connection of a voltmeter. If you will look at the line the current goes through and look at the line the voltmeter has right here where it's connected. These two lines are parallel, and so are these two lines. So we say that the voltmeter is connected parallel to this lamp, and that's what parallel means, okay? It just has to do with the shape, I think. So there you go. So ammeters are connected in series, voltmeters are connected in parallel. All right, now what are we going to do with this? I want you guys to look very carefully at this. There are three rules that a simple circuit such as this follows. Okay, three rules. Now, one of them we've already seen in our electric current notes, and that's this one, the potential rule. We know that what the source puts out, the load has to use up. No more, no less. We said that's another statement of conservation of energy. Okay? But there are some other rules. And I want you to notice one of them has to do with the current, one has to do with the resistance. So let's look at them. The current flow, when you have a simple series like this, the current flow is going to be the same through each device. It's like water through a pipe. There's only one pipe, so the current flow is the same through all of them. There's no forks in the road where some goes one way and some goes another. So it all travels around this loop, okay? So all the currents through each device is the same. That's another reason why it doesn't matter where we put that ammeter, because it's going to measure the same current everywhere. Now, the last one. As the electrons go through each device, they have to get pushed by the potential difference through the resistance of that device. So the total resistance met by any single one electron would be the total of the individual resistances in the circuit, however many there are. So R1, R2, R3, R4, however many. Now, right here, I want to remind you that devices such as the ammeter and the voltmeter, they don't use energy, so they're not included in the potential. They don't have the electrons aren't actually going through, well, they go through the ammeter, but that's because the ammeter measures the current flow. But this does not change the resistance, and therefore it doesn't change the current. This only measures the energy content per electron. So it doesn't change any of this either. So these are invisible to the circuit. So these three rules only pertain to the battery, which is converting chemical energy to electric, the light bulb, which converts electric to light, and the other light bulb, same thing, converts electric to light. So we only have these I's and R's for these three devices here because they convert energy. These are not converting energy, so they don't use potential, okay? They don't affect the current, and they don't have the resistance. All right. So now, let's take a look at this little problem that we're looking at. The first thing they want us to find is the potential difference used by this unknown bulb. Okay, now we can either do one of two things. We can use Ohm's law or we can use a trick. These are our tricks. So let's look at it. Well, we don't know, we do know the current going through this bulb, it's 2 amps, but we don't know its resistance or its potential. So in Ohm's law, we only have one out of the 3 variables, so we can't solve the formula if we say V equals I times R because we don't know R. Since we don't have enough to use Ohm's law, we have to go to a trick. What trick do we want to use? Well, we're trying to find the potential. So let's look at the potential rule. We know the total is the sum of the individuals, and look, we know the total is 8. This bulb uses 3 of the 8. So what's left for this bulb to use? The trick tells us, and so does our common sense, 5 volts of potential. Okay? 5 volts of potential difference. So now we know V2. Next item, it says, find the resistance of the filament in each bulb. Okay? Well, that's not going to be difficult because now we know V for each bulb and we know I for each bulb. So we can use Ohm's law now. So here we go. Hang on, let me get it straightened out. All right, so for R1, it has 3 volts of potential and 2 amps of current going through it, so it has 1.5 ohms of resistance. On the other hand, for the same current, the second light bulb has a bigger push. That means it's harder for the current to get, the current of 2 amps to get through that bulb for some reason. Because it needs a bigger push to create the same current, it has a bigger resistance, okay? The more push that's needed for that amount of current, the greater the resistance of that device. So this one has 1.5 ohms of resistance. This one has 2.5 ohm resistance. Now, if you look back up at the top, it does say that the third thing they want you to find is the total resistance of the circuit. Well, guys, guess what? There's two ways we can do that. We can use Ohm's law because we know IT is 2 amps and VT is 8 volts. So if you have a total of 8 volts of push and 2 amps of current, the entire circuit must have 4 ohms of resistance. Okay, now that we know the ohms, I want you to think, is there another way we could find the total resistance of this circuit? Aha, how many of you noticed? Okay, we could also simply add the individual resistances in the load, and that will give us the total resistance also. Isn't that kind of cool? So Ohm's law and the tricks allow you, it's like pieces of a puzzle, to figure out unknown information about a circuit, and it's pretty cool. Okay? All right, that ends our notes for today. And you're going to be looking tomorrow some more at resistance in the video and answering some questions. And then next week, we'll start doing diagramming and maybe a neat online lab thing that you all can do with it. All right, so have a good weekend.